a new video. So right now we're going to be doing math. Okay. So today we will be learning about RSA, full form, reversed Sharma-Adleman. Okay. Let's scroll down. So let me teach you what it does. Let's say you want to say math. This is how you would do it. In a RSA way. So like nobody can read it. You have to encrypt it and decrypt it, okay? Let's see every letter with a number under it. Let's see every letter with a number under it. The number is the position of the alphabet. See? So we want to say math. M is equal to, you see, 13. A is equal to 1. T is equal to 20. And H is equal to 8. So, you could say, oh, 13 what? 28. But the problem is too easy. People can guess this. A computer can find the answer to this 10 seconds, okay? At least 10 or at least 10 seconds. So this is how we'll do it. Well, so let's say you have a friend and you have 2 public keys and 1 private key. Tell your friend the public key. He'll encrypt the message. Then with the private key, you can decrypt it. This is how to do it. I'll tell you my public and private key so you guys know how to do it. Let's say this is public keys. Public keys. We'll call it N. N is equal to 779. I got this from Math Camp, so yeah. E is equal to 17. Private key. So my private key is 233. Oh wait, we'll call that D. D is equal to 233. We need this, okay. So this is how you encrypt it. Encrypt. So we get the number, like as you see, it says 13.1 right here. 13.120. We get the number to the power of E. That means, do you see this? That means power to the power of E mod or modulo N. And decrypt it. Decrypt is the number to the power of D modulo N. If they have your private key, then you're done for. Okay? So, let's encrypt it. Encrypt. Let me copy and paste this. Let's highlight that. So encrypt, we'll start with the number 13. 13 to the power of E. E is E is 17. To the power of 17 modulo n. I think it's 779. 779. Okay? Modulo 779, which is equal to, I'm not going to do that on the top of my head. So, let's see. Oh wait, a square and modulo calculator. Square modulo calculator. Power mod calculator. So, base. What was our base again? 13 to the power of 17. 13 to the power of 17 modulo 779. 779. Compute that. 193. 193. People will be like, what the hell is 193? So this is our first part of our message, right? First letter. Second letter. What just happened? What did I just do? Okay, right? First letter. It takes a while, but 1 to the power of 17 modulo 779. It is obviously 1, but I want to show you. I'm just going to show you. It's still 1. That's because 1 times 17 is still 1, and then modulo 7 is, yeah. You need to know what mod is, but I think I'm going to tell you on another video. So watch my next video, which will be like in 10 minutes, I think, or 5 minutes. But yeah, watch my next video and it'll explain modulo. 20 to the power of 17 modulo 779, which is equal to 20. Compute that 115. People would be like, what the hell is 115? Like, where did you get that number? And last but not least, 8. 8 to the power of 17 modulo 779, which is equal to 8. 449. 449. Another good thing about this is that, you know, math, right? Even though 8 is smaller than 20, the number is bigger. So, like, yeah, it makes the message, like, this is a weird message. 449. There you go. Is equal to math. This is to decrypt. So decrypt, we get the number to the power of d modulo n 779. So you see that the modulo is always 779. I don't know why that happens, but it just works. So let me 13 and 2, 3, 3. And 13. 440. Wait, what? Wait, what? Something happened. I don't know, but something went wrong. So let me try 1. 1 is obviously still 1. So 13. Why is 13 440? Oh wait! I'm so stupid. It's not 13. It's 193. It was 193, guys. Sorry. It is this number. We have to look at these numbers. Okay, so 193. 93. It's 13, right? Huh. What is 13? I wonder why it says 13. This is about to get interesting. You just saw me use the calculator. So, like, you saw me doing this. 779, which is equal to 1. Okay, now the next one, which is 115 to power of 17 to modulo 799. Oh wait, 779 modulo, which is equal to 115. 15, which is equal to 20. 20. 20. Is 20. Then the next one is 449 to the power of 17. Oh wait, it's not 17, it's 233 because 233 is our private number. So which is modulo 779, which is equal to, it should equal to 8. 449. And it's 8. And if we get back to our original question, and then this, oh, we have to go to the next page. But this, for some reason, magically comes back to this. We looked up here. It's another way of saying math. Now, it's another way of saying math. Which is better, saying math like this or saying math like this? This one there will be like M-A-T-H. But this they'll be stuck and they'll only find that as A. Here is something that I found out. It's over here. So see, maybe. This is a perfect example. There are two. So this is just D 1 2 3 A B C D E A B C D E. Oh, but this is way more better. I don't actually know how to decrypt it. No, I don't. I don't actually know how to decrypt this. How is D 1 when E is 1? What? Defend the east wall. Well, this is actually a perfect example. So these are actually two. I thought this was 1 2 3 4 1 2 3 4 5, but then I saw F, which is 1. Defend the east wall. They used to do this a lot. So there's this name called Julius. There's this person called Julius Julius Caesar. He made a cipher called the Caesar cipher, so he could lock like it's like A turns into B, and B is C, C is D, E is F, and so on. But there was a problem. They could just move the letter back 26 times, and then they could find the answer. So those things are called leaks. They show your fingerprint. Another one is if you search up and see how many times the letter E comes out, it's gonna be a lot. So that's a fingerprint. And after they solve all the E's, the fingerprint shows itself. So that's why we learned to do some stuff. So I'll show you my Khan Academy account. Okay, that was weird. But I don't know. I'm supposed to be signed in forever, but yeah. Okay. I got something. Let me just see. Photography. So here's it right here. The Caesar cipher. And like, this is what we learned today. Oh yeah, here's modulo. And yeah, the modulo. And this is what we learned. RSA, RSA encryption, RSA, and another RSA. So I'll show you them right now. If you don't have an account, you can just watch here.
Up until the 1970s, cryptography had been based on symmetric keys. That is, the sender encrypts their message using a specific key, and the receiver decrypts using an identical key. As you may recall, encryption is a mapping from some message using a specific key to a ciphertext message. To use the same key to reverse the mapping. So, for Alice and Bob to communicate securely, they must first share identical keys. However, establishing a shared key is often impossible if Alice and Bob can't physically meet, or requires extra communications overhead when using the Diffie-Hellman key exchange. Plus, if Alice needs to communicate with multiple people, perhaps she's a bank, then she's going to have to exchange distinct keys with each person. Now she'll have to manage all of these keys and send thousands of messages just to establish them. Could there be a simpler way? In 1970, James Ellis, a British engineer and mathematician, was working on an idea for non-secret encryption. It's based on a simple yet clever concept. Lock and unlock are inverse operations. Alice could buy a lock, keep the key, and send the open lock to Bob. Bob then locks his message and sends it back to Alice.
So this is
no keys are exchanged.
This is exactly what we're doing, but like in math, and we change it to numbers.
This means she could publish the lock widely and let anyone in the world use it to send her a message. And she now only needs to keep track of a single key. Ellis never arrived at a mathematical solution, though he had an intuitive sense of how it should work. The idea is based on splitting a key into two parts, an encryption key and a decryption key. The decryption key performs the inverse or undo operation which was applied by the encryption key. To see how inverse keys could work, let's do a simplified example with colors. How could Bob send Alice a specific color without Eve, who is always listening, intercepting it? The inverse of some color is called a complementary color, which when added to it produces white, undoing the effect of the first color. In this example, we assume that mixing colors is a one-way function because it's fast to mix colors and output a third, and it's much slower to undo.
It because we need to find we need at least
Alice first generates her private key by randomly selecting a color, say red. Next, assume Alice uses a secret color machine to find the exact complement of her red, and nobody else has access to this. This results in cyan, which she sends to Bob as her public key. Let's say Bob wants to send a secret yellow to Alice. He mixes this with her public color and sends the resulting mixture back to Alice. Now, Alice adds her private color to Bob's mixture. This undoes the effect of her public color, leaving her with Bob's secret color. Notice Eve has no easy way to find Bob's yellow since she needs Alice's private red to do so. This is how it should work. However, a mathematical solution was needed to make this work in practice.
Okay.
The solution was found by another British mathematician and cryptographer, Clifford Cocks. Cocks needed to construct a special kind of one-way function called a trapdoor one-way function. This is a function that is easy to compute in one direction, yet difficult to reverse unless you have special information called the trapdoor. For this, he turned to modular exponentiation, which we introduced as clock arithmetic in the Diffie-Hellman key exchange, as follows. Take a number, raise it to some exponent, divide by the modulus, and output the remainder.
Right now, I want to quickly explain what modulus is, or modulo. So it is just a divide. So let's say 2 module of 11. You do 11 divide by 2, and then find the remainder, which is 1. So 2 modulus 11 is just 1, because that's the remainder. It's actually really easy. I don't know why we don't learn this, but yeah.
This can be used to encrypt a message as follows. Imagine Bob has a message which is converted into a number, m. He then multiplies his number by itself e times, where e is a public exponent. Then he divides the result by a random number n and out.
So this is exactly what we did, remember? Right here. Right there. Let's say n is m. m e mod n. m e mod n. Magic.
Puts the remainder of the division. This results in some number c. This calculation is easy to perform. However, given only c, e, and n, it is much more difficult to determine which m was used because we'd have to resort to some form of trial and error. So this is our one-way function that we can apply to m, easy to perform but difficult to reverse. It is our mathematical lock. Now, what about the key? The key is the trap door, some piece of information that makes it easy to reverse the encryption.
Or in our way, the private key.
Need to raise c to some other exponent, say d, which will undo the initial operation applied to m and return the original message m.
Remember? Let's say c is the number. C is this number, power d, module n. Boom.
So both operations together is the same as m to the power of e, all raised to the power of d, which is the same as m to the power of e times d. E is the encryption, d is the decryption. Therefore, we need a way for Alice to construct e and d, which makes it difficult for anyone else to find d. This requires a second one-way function which is used for generating d, and for this, he looked back to Euclid. Over 2,000 years ago, Euclid showed every number has exactly one prime factorization, which we can think of as a secret key. It turns out that prime factorization is a fundamentally hard problem. Let's clarify what we mean by easy and hard by introducing what's called time complexity. We have all multiplied numbers before, and each of us has our own rules for doing so in order to speed things up. If we program a computer to multiply numbers, it can do so much faster than any human can. Here is a graph that shows the time required for a computer to multiply two numbers. And of course, the time required to find the answer increases as the numbers get larger.
But stays under
Notice that the
1 minute.
computation time stays well under 1 second, even with
1
fairly
second.
large numbers.
But
Therefore, it is easy to
Factor
perform.
takes
Now
much
compare this to
longer.
prime factorization. If someone told you to find the prime factorization of 589, you will notice the problem feels harder. No matter what your strategy, it will require some trial and error until you find a number which evenly divides 589. After some struggle, you will find 19 times 31 is the prime factorization. If you were told to find the prime factorization of 437,231, you'd probably give up and get a computer to help you. This works fine for small numbers, though if we try to get a computer to factor larger and larger numbers, there is a runaway effect. The time needed to perform the calculation
At first, it was shorter, but look now.
increases
Way
rapidly as there are more steps involved. As the numbers grow, the computer needs minutes, then hours, and eventually it will require hundreds or thousands of years to factor huge numbers. We therefore say it is a hard problem. due to this growth rate of time needed to solve it. So factorization is what Cox used to build the trapdoor solution. Step 1. Imagine Alice randomly generated a prime number over 150 digits long. Call this P1. Then a second random prime number roughly the same size. Call this P2.
So if you multiply it, so I'll tell you why you need this. The reason you need this is that these numbers are not random. These numbers are two random prime numbers multiplied together. So that's what they're doing. Multiply it to make n. N right there. One of our public
Multiplies these two primes together to get a composite number n, which is over 300 digits long. This multiplication step would take less than a second. We could even do it in a web browser. Then she takes the factorization of n, p1 times p2, and hides it. Now if she gave n to anyone else, they would have to have a computer running for years to find the solution. Step 2. Cox needed to find a function which depends on knowing the factorization of n. For this, he looked back to work done in 1760 by Swiss mathematician Leonhard Euler.
Don't say Euler wrong, because math people will hate you. Let's just skip all the way to step 4, the last step.
Therefore, it's easy. We now have a trapdoor for solving phi. If you know the factorization for n, then finding phi n is easy. For example, the prime factorization of 77 is 7 times 11, so phi of 77 is 6 times 10, 60. Step 3. How to connect the phi function to modular exponentiation. For this, he turned to Euler's theorem, which is a relationship between the phi function and modular exponentiation as follows. M to the power of phi n is congruent to 1 mod n. This means you could pick any two numbers such that they do not share a common factor. Let's call them m and n. Say m equals 5 and n equals 8. Now, when you raise m to the power of phi n, or 4, and divide by n, you will always be left with 1. Now, we just need to modify this equation using two simple rules. First, if you raise the number 1 to any exponent k, you always get 1. In the same way, we can multiply the exponent phi n by any number k, and the solution is still 1. Second, if you multiply 1 by any number, say m, it always equals m. In the same way, we can multiply the left side by m to get m on the right-hand side. And this can be simplified as m to the power of k times phi n plus 1. This is the breakthrough. We now have an equation for finding E times D, which depends on phi n. Therefore, it's easy to calculate D only if the factorization of n is known. Meaning D should be Alice's private key. It's the trapdoor which will allow her to undo the effect of E. Let's do a simple example to see all of this in action. Say Bob has a message he converted into a number using a padding scheme. Let's call this M. Then Alice generates her public and private key as follows. First, she generates two random prime numbers of similar size and multiplies them to get n, 3,127. Then she calculates phi of n easily since she knows the factorization of n, which turns out to 3,016. Next, she picks some small public exponent e. It's two random 1,100 factorization of n, which turns out to 3,016. Next, she picks some small public exponent e, with the condition that it must be an odd number that does not share a factor with phi n. In this case, she picks e equals 3. Finally, she finds the value of her private exponent d, which in this case is 2 times phi of n plus 1 divided by 3, or 2,011, plus 1 divided by 3.
So you can see how you get all of them.
Or 2011. Now, she hides everything except the value of n and e, because private exponent d
So how did they get
calculates phi of n easily since she knows the factorization of n, which turns out to 3016. Next, she picks some small public exponent e, with the condition that it must be an odd number that does not share a factor with phi n. In this case, she picks e equals 3. Finally, she finds the value of her private exponent d, which in this case is 2 times phi of n plus 1 divided by 3, or
So E is equal to the number without the prime factorization. In other words, if you factor it, this number isn't there. So D is equal to 2 times the phi of n plus 1 divided by E.
2011. Now, she hides everything except the value of n and e, because n and e make up her public key. Think of it as an open lock. She sends this to Bob to lock his message with. Bob locks his message by calculating m to the power of e mod n. Call this C, his encrypted message, which he sends back to Alice. Finally, Alice decrypts his message using her private key, D, accessed through her trapdoor. C to the power of D mod n equals Bob's original message M. Notice that Eve, or anyone else with C, N, and E, can only find the exponent D if they can calculate phi n, which requires that they know the prime factorization of n. If n is large enough, Alice can be sure that this will take hundreds of years even with the most powerful network of computers. This trick was immediately classified after its publication. However, it was independently rediscovered in 1977 by Ron Rivest, Adi Shamir, and Len Edelman, which is why it's now known as RSA encryption. RSA is the most widely used public key algorithm in the world, and the most copied software in history. Every internet user on Earth is using RSA, or some variant of it, whether they realize it or not. Its strength relies on the hardness of prime factorization, which is a result of deep questions about the distribution of prime numbers, a question which has remained unsolved for thousands of years.
I want to tell you something very important. Some companies, they lost their private key number, and then they had to reboot the whole website. But that's all I'm going to talk about. Brandon out!